So hi everyone, we are here to talk about real-time inference of neural networks. This means we will show you all necessary steps to take a trained model out of Python and to put it in a real-time environment, for example, an audio plugin. And for that, we rely on 3 inference engines, ONNXRuntime, TensorFlow-lite, and LibTorch. And just something to note, we will cover this whole topic from a programmer or DSP perspective, and we don't presume any deep knowledge of neural networks. So, what's our background? As we had prior knowledge in implementing neural networks in audio plugins, we decided to participate at this year's neural audio plugin competition run by the audio programmer. And we did it with a group of fellow students under the name Torsion Audio. And we developed a plugin called Cyclone, an automatic drum layering plugin, where we utilized the Rave architecture, which was developed by IRCAM. And yeah, we won the competition, and then we decided we want to show you what techniques we use to implement that, and by preparing this talk, we also refined our methods. To short introduce ourselves, my name is Valentin Ackva. I'm currently studying towards my master's in audio communication and technology in Berlin. Besides that, I work as an audio software developer at InZone in Germany, which is an intelligent audio optimization company focusing on communications. There, I'm responsible for developing classical DSP audio effects, but also newer effects for tasks like denoising or audio super resolution.
Hello, I am Schulz, and I also study towards my master's degree in audio communication and technology. And besides that, I also work at the Institute as a student assistant, and we are doing research there in Linux audio systems, spatial and network audio systems, and also in AI with plugins. Besides that, I also work as a DSP engineer for medical devices and mostly doing denoising there with and without AI.
So, let's directly dive into the topic. In the last years, a lot of neural networks came out in the audio domain. And for simplicity, we decided to categorize these into 4 types. The first one is waveform modeling. That's a neural network that usually takes an input signal, processes through the model, and gives us an process output. Then we have differential signal processing. These are usually types that take in an audio input, and the network predicts some parameters for DSP algorithms, for example, oscillators or filters. Then we have the classifiers. These are meant to classify an incoming signal into specific categories, for example, an animal classifier or also like pitch estimators. And the last one is transcriptors. These are meant to transform an incoming signal into a specific output format. Example here is basic pitch, which transfers audio to MIDI. In our talk, we will focus mainly the waveform modeling methods, but all we will show you today is also adoptable for the other types. So, what's our table of content? We first start with a short introduction into deep learning, then show you what inference engines exist. We show you how to use them in a minimal example, and also in a streaming architecture where we show you how to deal with plugins and these engines. Then we give you some expertise regarding benchmarking these kind of models, give you techniques how to continuous process model with audio, and in the end, give you an outlook with further improvements you can go.
So, thank you. Let's start with the first chapter. It's called Deep Learning Lead-In. It's a very brief introduction into deep learning. We will not cover the topic in depth. It's more like a motivation to understand the very basics. So I will leave out a lot of subjects, so just you know when you're hearing this chapter. So we will start by our familiar audio buffer. It's our input audio buffer. It's made out of floats or doubles, and it has the length m. So when we process this input audio buffer to the most simple neural network, how would this look like? Well, actually, this is like a matrix multiplication. This is a one dense layer, one linear layer neural network, and this is the most simple one. And if we process our model input, we multiply it by a weight matrix, and then we get an output signal. And the weight matrix, or the weights inside of this weight matrix, is the parameters that we are tuning during our training. So we adapt those weights so that we get the output signal that we want to have if we input a certain input signal. When we talk of inference, we have an already pre-trained model. So we have all those weights, how we want to have them, and we feed forward our input signal through the neural network, in this case, through this matrix, and then we get an output signal. So there's no more training happening there. We are feeding forward our input signals, processing the data. So most neural networks have more than one layer. Here we have a little different graphical representation. We are having our matrix multiplication on the left side here. We have the weights now as turquoise lines. And we changed the notation a little bit. So our output signal we notate now with Z, which we had in the beginning, here on the most left side with the index 0. And now if we have different layers or more layers in our neural network, we will have further matrix multiplications. So we have other matrices with other weights, and then we feed forward our input signal through the neural network and get an output signal, which we notate again with Y. And in the middle, we have this Z layers, and we call them hidden layers because they are inside of the neural network. So then there exist also more complex layers, so that doesn't necessarily need to be a simple matrix multiplication, but we can also have convolution layers, for example. Here we have different convolution kernels, which are also made of weights, and we convolve our input signal with those convolution kernels, and we get an output. So in this case, we have 3 convolution kernels, and we have a matrix as output. Then we have other layers, which are even more complex, maybe. So we have recurrent layers. This is an LSTM layer. And the point of this recurrent layer here is that it feeds back in the input signal into the neural network, or into the next cell, so-called cell. But let's stay with this for the layers, and let's think about the required information in order to inference an input signal through a neural network. So what do we need to know in order to have the output signal that we want to have with our trained neural network? So first, we need to know the weights of each layer. So those are the values that we tuned, so our neural network gives us the right output. Then we also need to know the input shape of our audio input buffer. We need to know the types and the orders of the layers in our network. So if we have a dense layer first, then we have a convolution layer, then another dense layer. We need to know their shapes, and we need to know the specific characteristics of each layers. So we have activation functions, for example, for dense layers, we need to know them, and for example, convolution layers have also specific characteristics, like stride, for example. We need to know all of that. And then finally, we have our output shape, which we need to know. So this is all the information that we need in order to successfully inference our neural network. How would this look like in an example, for example, if we export all of this information into a JSON file? It would look like this, for example. So on the top left, we have our input shape. And then we have the first layer, which is a convolution 1D layer. And then we have all of those weights, which are simply float or double values. So that has been trained during the training. And now the question arises, how can we make our inference, or how can we implement our inference inside of our real-time critical audio environment? And how's the pipeline in order to do this? So first we need to train our neural network. The training is usually done in 2 big machine learning frameworks, PyTorch or TensorFlow. This is usually done in Python, but this is outside of our scope for now, for this talk at least, because we cannot cover everything. We focus on inferencing neural networks. So we will talk about the export of our neural network model, and we will talk about the implementation in a real-time critical environment.
So, now we are going to talk about inference engines. And these engines are responsible for loading our trained model and then allow us to feed in our discrete input signal, process it, and get the process output. So, before we start into talking about inference engines, we want to mention that there are actually 2 ways to go from here. Either you write the inference completely by yourself. This means you look in your model, look which layers were used, and then You can start implementing from scratch. That you can use like specialized libraries like Eigen or use SIMD instructions to speed up the process. Or you can use these specialized libraries that have already implementation for the most common layers and are often optimized to perform the model. And of course, we will focus on that in this talk. So we cover in our talk ONNXRuntime, LibTorch, and TensorFlow-lite. In the audio domain, there are also other engines you can use, for example, RT Neural, which is really performing well on small networks, or Tract, which is an inference engine written in Rust. When we consider we have all these different operations in Python in these models, is this export process loading into these engines a straightforward process? And unfortunately, it's not. It's a bit complicated, and we show you why. To say, it's quite convenient to convert a model within the framework. So if you train your model in PyTorch, LibTorch is an obvious choice. You can go. The same is for TensorFlow and TensorFlow-lite. If you look at ONNX, this engine is meant to inference models from both frameworks. But what you want to avoid is converting a PyTorch model to TensorFlow-lite. It's possible, but it can get complicated. But there are also some things you have to consider when converting inside a framework. Let's look at TensorFlow-lite. Here in Python, we have our core operators, which you can use to train your model. But the C++ inference engine only has a substract of these operators. So if you need some of the core operators, you have to manually compile an im. And also, if your model has some custom operators that are usually layers written by a machine learning engineer and is differing a bit from these common layers, then you also have to manually write that layer from scratch in C++. When we look at LibTorch, here the process is a bit more convenient. LibTorch almost supports all layers which are available in PyTorch, and even custom layers are easily integrated because there is a wrapper called TorchScript which can load these Python-written custom layers. Here's just something to be aware of. If your PyTorch model uses some additional libraries like Torch Audio, these are not included. When we look at ONNXRuntime, this engine can convert PyTorch to ONNX, but here not all layers are supported. When you come from TensorFlow, pretty all layers should be covered. And also here in general, if you have custom or unsupported layers, you have to manually write them from scratch. Now let's look at the efficiency. This is one of the most crucial aspects when choosing an engine because, we are processing a lot of data through it. And we took here a comparison from the last DFX conference. And here 3 classifier models were benchmarked. They differ from their model size. And what we can see is that LibTorch is the slowest engine for all different sizes. And in some cases, even 4 times slower than its competitors. If we look at ONNX and TensorFlow-lite, we see that they have quite similar numbers, but ONNX is performing a bit better on larger networks, while slower networks run faster on TensorFlow-lite. If we look at the model and library footprints, we see that the model size is not making a huge difference across this engine, but the library footprint does. LibTorch, for example, has around 200 megabytes, while the others are way, way more smaller, and that's just something to consider when shipping your plugin. So, what's the takeaway of this chapter? If you have custom layers written in Python, LibTorch is an obvious choice, but if you want to prefer inference speed, you should rather use ONNX or TensorFlow-lite. To mention, most common layers used in the audio domain are covered by all of these engines. And also note, they all come with a license you can use in commercial products.
So, thank you, Valentin. So now hopefully we know which backend we want to choose, and we can start with our inference. But one thing to consider first, we need to export our model. So let's get back to the pipeline. Export first, and then implement into our real-time critical audio environment. So how's the export looking? Well, the export is actually quite some boilerplate code where you can add some options, and if you respect all the things that Valentin has said, so you only have layers inside of your neural network, which are also supported by your inference engine, that should be quite easy. So now we can start with our inference, and we will start with a minimal inference example. So how is the inference pipeline? First, we will load our model inside of our inference engine. Then we will define some options and allocate some memory. And in the next step, we can take our input data, transform it into an input tensor, which is the data type which our inference engine utilizes. Then we can make our inference, get an output tensor, and from this output tensor, we can extract our output data to further process it. So this is a minimal inference example in ONNXRuntime. We have here on the first page, we have the model which is being loaded, and we are defining some options. So for example, we are assigning this model to the CPU. So we want to utilize the CPU. We can also utilize the GPU in ONNXRuntime. And in the second step, we will take our input data, make an input tensor out of it, which has a specific shape. Then we will run our inference, get back an output tensor, and as the last step, we will extract our data from this output tensor. So the question which arises now is this inference example actually real-time safe? And no, this inference example is not real-time safe. And it's not real-time safe because of multiple reasons, but the main reason here is our inference method. So we have the run method for inferencing in ONNXRuntime, and here we are constantly dynamically allocating space. So we are not only dynamically allocating space in the first run method, but we are dynamically allocating space all of the time, allocating memory all of the time during our inferences. And since we need to run those inferences in our audio callback, this is not possible because it's real-time, it's not real-time safe. So those dynamic memory allocations are happening because ONNXRuntime, inside of ONNXRuntime, inside the library, it is always reshaping its tensors, and it's reshaping its tensors from layer to layer. So different layers have different shapes, and internally, it's resizing those tensors, and that's something we cannot do on our real-time audio thread. So considering that actually none of those inference engines are giving any real-time guarantees in regards to audio callbacks, how can we circumvent these issues and utilize them anyway?
Well, for that, to circumvent these real-time safety issues, we want to present you an architecture that can stable run these inference engines in a plugin. And for that, let's hop into the architecture. So in this architecture, we have on the left side our real-time audio thread with our audio processor. We choose here as a base plugin, but this architecture can be adopted to any other framework or audio type. And here we have our prepare to play and process block functions. We have the host buffer size, which can be any number, usually a power of 2 number. And on the right side, we have our inference thread. We separate it into a separate thread. And here we can run our inference safely. And here the number we have is the model input size. And this number determines how many samples are necessary to run one inference. And this whole architecture allows us firstly to run the inference stable on a separate thread, but also to hand over the audio data in chunks we need for the inference. So in the next step, we need some thread-safe buffers in between these threads to share audio. And why do we need thread-safe buffers? We just learned a session earlier here. But the problem is, if we don't use thread-safe buffer, we get problems like potential data corruption, ordering issues. And to solve this, there are usually 2 approaches. A common approach would be to use mutexes or logs, but since we're here on the real-time audio thread, we can't use this kind of stuff because they have also non-deterministic runtimes. So we have to use some log-free solution here. And there are a lot of ready solutions out there. We choose an implementation from Cameron, which is linked down below. And with that, we can go back to our proposed architecture. When we call prepare to play, we will allocate all the memory, especially these thread-safe buffers, and then start the inference thread Once the audio callback started, we will push our audio samples into the first buffer. And the next step, the inference thread can now constantly check, has our first buffer enough samples to start an inference? And if so, we extract the data, start in pre-processing if necessary, inference, post-process, and write it back to the second buffer. Once that happened, we go back and check again, hey, do we have already enough samples to start the next inference? When we go back to the real-time audio thread, once we pushed the samples into the first buffer, we will immediately check if the second buffer has already processed audio, and if so, we extract it and return it to our audio processor. But what happens if we don't have enough samples in our second buffer? In this case, we have to return something, so usually an empty buffer, but this should never happen. And how can we solve this problem? First, to understand this problem, we have to know, in our first run, for example, we push audio into the first buffer, and then immediately check in the second buffer, do we have already processed samples? And since the inference thread will never run inference that fast, we have to introduce here some latency. And how much latency do we have to introduce here? Well, that depends on our audio configuration. So the model input size plays a role here, the host buffer size, but most importantly, the max inference time. This is the time one inference takes to process the data. Yeah, this all should ensure that we have a stable continuous audio flow, but what happens if we still run out of samples? Our introduced latency should compensate that, but if we really still continuously run out of samples, this is an indicator that our neural model is probably too heavy way to process in real time. And then we can go to approaches to either reduce the model complexities, so remove some layers or move them together, smaller the hidden size, or try to process more data at once. So increase your model input size or use techniques like batching. But if you do so, you will increase your latency of your plugin. Yeah, this is the overall architecture. We will upload later the code and the slides for that. And the next step, we talk now here about that latency we add. And the numbers that plays a role, the host buffer size, the maximum inference time, and the model input size. How can we calculate these latency? Well, here we have a quite similar equation. It depends on three conditions. First, we divide the host buffer size by the model input size. And if the remainder is 0, we just take the maximum inference time. If the remainder is smaller than the whole buffer size, then we have to also add the host buffer size. And if it's greater, then we have to add the model input size. And with that, we can calculate the additional latency. And this will also be the overall latency of our plugin. And then we can tell our DAW to compensate that latency. So, since this maximum inference time plays a really important role here, how can we define this number?
So the solution that we propose to define this number is benchmarking. And here with benchmarking, we can find our maximum inference time, but we can also make sure that our inferences are running continuously and smoothly on the inference thread, and we are not running into the problem of having missing samples. So how to benchmark first, or how did we realize our benchmarks? Since we take the CMake build structure, build architecture, we were realizing our benchmarks with C-tests, and as backends, we utilize Google Test and Google Benchmark. And what did we benchmark? We benchmarked our process block callback, including our inference thread, and we were doing multiple repetitions in order to find the mean inference time and also the maximum inference time. So now we see our first benchmark here, and this is a benchmark on a similar TensorFlow and PyTorch implementation of a neural network, which has been presented by Wright et al. In the paper Real-Time Guitar Amplifier Emulation with Deep Learning. The TensorFlow implementation has been done by Mr. Keith Bloomer, also known as Guitar ML. And the PyTorch implementation, the similar one, has been done by us. So we are benchmarking the inference time for different buffer sizes, and those buffer sizes are simulating the host plugin buffer sizes. And first, I want to draw your attention to the line on top. So the gray straight line on top, this marks our real-time threshold. And this is dependent on the sample rate, and this determines the time we have to process one buffer. And now, first of all, we need to make sure that our straight lines, which represent here the mean for all of the 3 inference engines, are below this real-time threshold, because otherwise we will continuously run out of samples. Now we also have the dashed lines. The dashed lines are representing the maximum inference times. So this is actually a non-deterministic time because of the dynamic memory allocation, which I was talking earlier. The communication with the operating system, we don't know how long this dynamic memory allocation will take. And we have done here 4,000 repetitions, I think. So we hope to estimate this maximum inference time right, so that we can smoothly run our inferences and add this maximum inference time to our latency calculation, which Valentin was talking about earlier. So this is a benchmark on an Apple MacBook Pro with a M2 chip, and now we will see the benchmark on a Windows 10 laptop looks pretty different. It's a little interesting here that this mean inference times seem to converge to a minimum, no matter how small we are making the buffer size. But we are showing you this second benchmark here because we want to point out that those maximum inference times and also the minimum inference times can be very different from one operating system to another operating system and also across different consumer laptops. So when you plan to ship your plugin to your consumers and have different operating systems that you support, we recommend to make sure to benchmark all of those operating systems and adapt those maximum inference times accordingly. And so now one last thing, you cannot benchmark all the buffer sizes which are possible, of course, and we benchmarked only multiples of 2 here. And so we recommend to you just to interpolate between 2 buffer sizes when the host plugin, the host is transferring a buffer size which you have not benchmarked.
Okay. In the last chapters, we showed you how to run these inference engines stably in a real-time environment. But next to a stable plugin, we also need to have a continuous signal flow. And since audio processing with neural networks can introduce some artifacts, we want to show you some techniques how to solve them. So for this example, we go back to our Cyclone BST plugin we programmed, and here's important to understand how we process data here. So we have our inference, which takes a certain number of samples, for example, 1024 samples. We run the inference and get 1024 output samples. And in the next inference, we take the next 1024 samples, and so on. And here we encountered some problems. First of all, on the left side, we see the input signal, and the other 2 images are the output signals with different model input sizes. And what we can see here that our input signal is way better reconstructed when using a higher model input size. So that's just something to be aware. You probably want to have the smallest model input size, since this will have a lower plugin latency. But some models need a higher amount of samples to get a nice output. But what we also encountered are boundary discontinuities. So at the beginning and the end of each processing buffer, we had 0 crossings. And these were related to our processing in our neural network. Here we have some 0 paddings, and these 0 paddings in the neural network introduce that 0 crossings. And how can we solve that? Well, if we want to have a DSP solution for that, we can use a technique like overlap and add, where we divide the incoming signal into smaller chunks, process them, they have a certain amount of overlap, process them through the neural model, apply a windowing function on it, most of the time a hand window or a rectangle window, and then we can sum them together to a continuous output signal. And through that, we will get rid of that first and last samples. And just something to consider here, if you use that technique, use a periodic window, and in some cases, you also have to normalize your buffers. I forgot something. Where should we place that in our architecture? So it's quite simple. We have already implemented that in our pre- and post-processing.
So now the question arises, are there also solutions on the neural network side in order to solve those boundary discontinuity problems? And yes, there are solutions actually, and yes, actually the authors of Rave have already implemented those solutions in their neural network model. But their neural network model was written in PyTorch and was utilizing custom PyTorch layers as a solution for making the model streamable. And since we in Cyclone utilized ONNXRuntime as inference engine, those layers were actually not supported. So there were custom one-dimensional convolution layers, which ONNXRuntime was not supporting, so we needed to find another solution. If we would use LibTorch as inference engine, well, we would support those layers. And I just want to take you and maybe we can understand how these layers are working. So in order to understand this, first we need to understand the difference between causal and non-causal convolution layers. So Valentin has already said, inside of the neural network, there is zero padding happening. So this zero padding was actually the reason why we had those boundary discontinuities, because in those convolution layers, we were adding zeros to the beginning and end of the signal, and those were causing this zero crossings, which were always happening in the beginning and in the end of one block. So now there are two types of zero paddings for convolution layers. There is the causal zero padding, which is only zero padding the past or the left side, and there's also the non-causal zero padding, where we are padding the left and the right side, so the so-called future, maybe the right side. So how can we make a causal convolution streamable, or a causal convolution layer? Well, the solution for that is quite straightforward. We are caching the most recent samples and add them as zeros for our next block. This way, we don't have those zeros crossings anymore, and we can make our neural network streamable. But unfortunately, most neural networks are not utilizing causal convolution layers, but rather non-causal convolution layers. So how can we make those convolution layers streamable too? Well, the authors of Rave have presented this, this custom PyTorch layer. And the first step in order to make a non-causal convolution layer streamable is actually to make this non-causal convolution layer causal. And here they presented this approach. So we take the zeros from the right side and add them to the left side in order to make this convolution layer streamable. But in order to not alter the computational graph of the neural network, we need also to respect some peculiarities there. So for example, if we have parallel branches in our neural network model, we need to add additional delays. Or if we have strided convolution layers, there are also some additional delays which need to be added. But we will focus on this very simple non-causal convolution layers with only 1 0 at the beginning and at the end. And this is quite straightforward. We can just take it to the left side. And now we have our causal convolution layer. And with this, we can make it streamable again. So this solution can also be done after the training process to make those non-causal convolution layers streamable. So that's quite cool, I think. But I want to mention one thing here, and this is that this solution will introduce some additional latency. In this case, we have an additional latency of 1 sample, as you can see here. And because we utilize quite big convolution layers and lots of zeros in bigger networks, you need to be aware that this really can introduce a lot of latency. And for example, the neural network model Rave can be trained in a non-causal way and in a causal way. And if we train Rave in a non-causal way and then make this rave model streamable afterwards, we will have a latency of 650 milliseconds. If we train the rave model in a causal way and make it streamable afterwards, we will only have a latency of 50 milliseconds. So you see, there is a quite big difference there, and therefore we recommend to you, whenever you have convolutional layers, and you can make them, you can train them causally, and you want to make your model streamable afterwards, and you care about the latency, then try to train your network in a causal way. So now we come to the last part of the presentation. So first we're going to have a short outlook. And yeah, we want to talk about how we can further optimize those neural networks, or we want to give you some keynotes at least, so you can optimize your neural network model on the model side, so in the training process, but you can also optimize our architecture, or in the real-time environment, optimize the network there. So those are only some keywords. We will upload the slide afterwards, Valentin already said. So if you need a starting point to further optimize your neural network, here are some points. And finally, we come to the very last part of this presentation. So we want to share with you our repository. And yeah, there's the QR code here, so you can scan it and get to our repository. And this repository is actually a template for implementing a real-time safe, real-time safe inferences inside of an audio plugin. So for now, we have implemented this model, which we already benchmarked also. So from the paper, real-time guitar amplifier emulation with deep learning, a model which implements the architecture which has been presented in this paper, but it is meant as a template so you can easily implement all sorts of neural network models inside a plugin. For now, we have only Juice as a framework, but we also plan to support other audio APIs. So we can now have a look at the plugin, hopefully. And yes, so this is our plugin. We will have the input signal, which will be just some guitar playing. And then we will introduce our neural amplifier model. And afterwards, we will switch between the inference engines. And in our plugin, you can switch between all of those three inference engines seamlessly. Oh? It's audio device is off, okay. So that should be the right audio device. The dry signal here. Adding the amp model. Running the inference with ONNXRuntime, LibTorch, and TensorFlow-lite. Back to the presentation. So you can see we have implemented all of those three backends, and that's not a plugin that you want to ship to your consumers, because you don't need three backends at once. It's really a template plugin, so whatever neural network model you have and whatever inference engine you are planning to use, you can use this template and hopefully start with your inference right away and not care about implementing this whole architecture. So, and it's all free, the code is all open source, and we would actually love to see some of you contributing to this plugin template, whether it's just by sharing some bugs that you find, or by contributing to the code base, or also to share some benchmarks. Because inside of this repository, we have those C-tests available, so you can benchmark all of your neural network models, and maybe we can find out which neural network model is running fast on LibTorch and which one is running fast on TF-Lite. So yeah, maybe you want to participate in that, and we would be really happy if you want to. And with this, we want to thank you for your attention, and if you have any questions, now it's the time.